After discussion of the carbon compounds, their reactions for group 14 elements, the lightest element, now we come to the heavier group elements of group 14. Although silicon, germanium, tin, and lead in their +4 oxidation states often form binary compounds, the structure and properties of these compounds are usually significantly different from those of the carbon analogues. Silicon and germanium are both semiconductors with structures analog to diamond. Tin has two common allotropes. White beta tin has a metallic lattice and metallic properties, whereas gray alpha tin has a diamond-like structure and is a semiconductor. The metallic beta form is stable above 13.2 degrees centigrade, while the non-metallic alpha form is stable below 13.2 degrees centigrade. Lead is the only group 14 element that is metallic in both structure and properties under all conditions. Based on its position in the periodic table, we expect silicon to be amphoteric. In fact, it dissolves in a strong aqueous base to produce hydrogen gas and solution of silicates. But the only aqueous acid that it reacts with is hydrofluoric acid, presumably due to the formation of the stable SiF6 2-I. Germanium is more metallic in its behavior than silicon. For example, it dissolves in hot oxidizing acids such as nitric acid and sulfuric acid, but in the absence of an oxidant, it does not dissolve in aqueous base. Although tin has an even more metallic character than germanium, lead is the only element in the group that behaves purely as a metal. Acids do not readily attack it because the solid acquires a thin protective outer layer of Pb2 plus salt such as lead sulfate. All group 14 dichlorides are known, and their stability increases as the atomic number of the central atom increases. In dichlorocarbene CCl2, a highly reactive short-lived intermediate then can be made in solution, but cannot be isolated in pure form using standard techniques. SiCl2 can be isolated at very low temperatures, but it decomposes rapidly above minus 150 degrees centigrade. And germanium chloride is relatively stable at temperatures below 20 degrees centigrade. In contrast, stannous chloride is a polymeric solid that is indefinitely stable at room temperature, whereas BbCl2 is an insoluble crystalline solid with a structure similar to that of stannous chloride. The stability of the group 14 dichlorides increases from carbon to lead. Although the first four elements of group 14, they all form tetrahalides, that is MX4, with all the type of halogens. Only fluorine is able to oxidize lead to the +4 oxidation state that forms PbF4, lead tetrafluoride. The tetrahalides of silicon and germanium react rapidly with water to give amphoteric oxides, where Am is either silicon or germanium. The reaction is shown as MX4 that can be solid or liquid, reacts with water to give MO2, that is dioxide. In contrast, the tetrahalides of tin and lead react with water to give hydrogen metal ions. Because of the stability of its +2 oxidation state, lead reacts with oxygen or sulfur to form PbO or PbS, lead oxide or lead sulfide respectively, whereas heating the other group 14 elements with excess O2 or acid gives the corresponding dioxides or disulfides respectively. The dioxides of the group 14 elements become increasingly basic as we go down the group. Because the Si-O silicon oxygen bond is even stronger than that of the C-O, that is carbon oxygen bond. Here we can compare their energy values, that is 452 kilojoule per mole versus 358 kilojoule per mole. Silicon has a strong affinity for oxygen. The relative strengths of carbon-oxygen and silicon-oxygen bonds contradict the generalization that bond strength decreases as the bonded atoms become larger. This is because we have thus far assumed that a formal single bond between two atoms can always be described in terms of a single pair of a shared electron. In the case of silicon-oxygen bonds, however, the presence of relatively low energy empty d orbitals on silicon and non-bonding electron pairs in the p or sp hybrid orbitals of oxygen results in a partial pi bond. This we can see due to its partial pi double bond character. The silicon-oxygen bond is significantly stronger and shorter than would otherwise be expected. So this is the very prior important reason. A similar interaction with the oxygen is also an important feature of the chemistry of the elements that follow silicon in the third period, just like in phosphorus, sulfur and chlorine. Because the SiO, that is silicon oxygen bond, is unusually strong, silicon oxygen compounds dominate the chemistry of silicon. So this is why we see a large number of silicon oxygen compounds just like carbon chemistry. Because the silicon oxygen bond is unusually strong, the pi bonding between silicon and oxygen silicon has relatively low energy, empty 3d orbitals that can interact with filled 2p hybrid orbitals present on the oxygen atom. This interaction results in a partial pi bond in which both electrons are supplied by oxygen, giving the silicon-oxygen bond partial double bond character and making it significantly stronger and shorter than expected for a single bond. So this is the explanation given for the unusual silicon-oxygen bond strength. This is the structure. We see how partial pi bonds are formed between the 3d orbitals of the silicon and 2p orbital of the oxygen. This shows the pi bonding between the silicon and oxygen atoms and their empty free orbital of 3d of silicon, while filled orbital with 2 electrons in oxygen present in 2p orbital. Compounds with anions that contain only silicon and oxygen are called silicates. These are also the very important compound formation useful in the daily life, whose basic building block is SiO4 to the power 4 minus. This is a basic unit which form the chain of long silicates with either one bridging oxygen atom or two bridging oxygen atoms in different various forms. The number of oxygen atoms shared between silicon atoms and the way in which these SiO4 4 minus units are linked vary considerably in different silicates. Converting one of the oxygen atoms from terminal to bridging generates chains of silicates, while converting two oxygen atoms from terminal to bridging generates double chains. In contrast, converting three or four oxygens to bridging generates a variety of complex, layered, and three-dimensional structures respectively as shown here. These SiO4 4- units are arranged in with the help of one bridging oxygen atom above and below. Structure shows the two bridging oxygen atoms forming the various type of bridging from terminal to double chains. Converting three or four oxygen atoms also in the bridging, which generates the three-dimensional structures of the silicates. So these are the various forms of silicates, and we will continue it in the next part of this topic.